أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. Dear student, Assalamu alaikum. My name is Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. Today the topic of our presentation is infrared spectroscopy. The course code is CHEM451 molecular spectroscopy. So whenever organic chemist or even chemist want to know about the structure of any compound, so means the job is to determine the structure of organic compound, how we can have some information about the structure of an organic compound. This because with this, by knowing the structure of organic compound, we know that how atoms are connected together. Means whether it is by single bond, double bond, triple bond, whether it is connected to which atom, means hydrogen is attached to oxygen or carbon or some other atom, and which type of bonds, by single bond, sigma bond, pi bond, double or triple bond, and what functional group exists in the molecule. For example, OH is attached, means this is alcoholic group. Carboxylic acid is attached, carboxyl group, or ketone or ether or any functional group attached in this compound. If we have a specific stereoisomer, whether this is a cis isomer or trans isomer, so we know from from these information. Yes, analytical chemist can answer, or at least can attempt to answer these questions. But how? There are instrumental method of structural determination, and this instrumental method of structural determination, spectroscopy, is one of the most important technique. Inside the spectroscopy is the interaction of radiation, electromagnetic radiation, with matter. This study is basically spectroscopy. One of the spectroscopic method is ultraviolet spectroscopy, which is shortly called UV spectroscopy. We have discussed this spectroscopy in details. What happened in UV spectroscopy? Promotion of electron. When UV radiation interact with matter, so what happened? Promotion of electron to high energy level through irradiations of the molecule with ultraviolet light. So when these electron goes to the higher energy level, it absorb a certain amount of radiation, certain amount of energy in the form of radiation. So when it is coming back to the lower energy state, stable state, either this absorbed energy is measured or this emitted energy is measured. So emission spectroscopy and absorption spectroscopy. So in UV, we are measuring the absorption spectroscopy, which is used for the promotion of electrons. So that's why it is called UV absorption spectroscopy. This spectroscopy provides mostly information about the presence of conjugated P system and the presence of double and triple bonds. The next one is nuclear magnetic resonance spectroscopy, shortly called NMR. So what happened in NMR? Instead of UV radiation, in NMR, radio frequency radiations are used for the excitation of nucleus instead of electron through radio frequency radiation. And this is a purely qualitative technique, and it provides a very detailed and extensive information about the molecular structure and the atom's environment, basically atom's connectivity, that what type of different hydrogens are present in the molecule because it is having a different environment. What type of different carbon are attached in the molecule? We are doing proton NMR, carbon NMR, etc. The next one is mass spectrometry. Although the radiations are not involved in a mass spectrometry, that's why it is not called spectroscopy, but it is a quantitative as well as a qualitative technique. We know about the quantity and a quality of analyte. Quality of analyte means what is the analyte, which type of analyte it is, and about the structural information from the fragmentation pattern of the molecule. So bombardment of sample with electrons and the detection of resulting molecular fragments. So provides information about the molecular mass, also the structures means atom connectivity. The next one is infrared spectroscopy. In today's lecture, we are focusing on IR spectroscopy. So basically in this spectroscopy, IR radiations are used for triggering molecular vibration through radiation with infrared light. Provides mostly information about the presence or absence of certain functional groups. Dear students, we know that we have discussed already in this course this ultraviolet spectroscopy in detail. Also NMR in our previous two lectures. Also, we have discussed mass spectrometry in the other course 451 and 451, yes, or 453. And we will discuss this IR spectroscopy. Basically, in this spectroscopy, this physical stimulus means radiations, whether UV, radio frequency, IR, is interacting with the molecule. So I'm telling you the basics of spectroscopy. This physical stimulus means this is interacting with the molecule. So, and the result of this physical stimulus, this radiation, this interaction of this radiation with the molecule, different molecules, according to the radiation, to the physical stimulus, respond. So, what we do, we are detecting the response of this molecule by instrument, like by UV absorption spectrometer, like by NMR spectrometer, by IR spectrometer. So we are measuring this response. This is this visual most common representation, or then it is we are getting from this measuring this response, we are getting a spectrum, and then we are getting the desired or required information from the spectrum. So upon radiation, we are summarizing it. Upon radiation, with infrared molecule, coming to our topic of discussion, IR spectroscopy. Upon radiation with infrared light to this molecule, certain bonds in this molecule respond by vibrating faster. This response can be detected by the instrument and translated into a visual representation on the paper, which is called a spectrum. So, what we do in a spectrum, whenever we are interpreting spectrum, so we are basically recognizing a pattern, and this then associate this pattern with some physical parameters, and then identify possible meanings, purpose explanation. We are extracting our desired explanation from this associated pattern with this recognized pattern. This physical, the pattern is associated with a physical parameter, and then we are possibly extracting those information what we need for the identification or quantification of any molecule or any analyte. So once a spectrum is obtained from the instrument, the main challenge is to extract information, purpose explanation. It contains an abstract or hidden form. This requires the recognition of a certain pattern first, the association of this pattern with a physical parameter, and then interpretation, extracting out the purpose explanation of these patterns in terms of meaningful, scientific, and a logical explanation from this spectrum. What is electromagnetic spectrum? Most organic spectroscopy uses electromagnetic energy or radiation is the physical stimulus. As I told you, physical stimulus, interaction with molecule respond. So most organic spectroscopy uses electromagnetic energy or radiation as the physical stimulus. Electromagnetic radiation, such as visible light, has a no detectable mass component. In other words, it can be referred as a pure energy. Other type of radiation, such as alpha rays, which consist of helium nuclei, have a detectable mass component and therefore can't be categorized as electromagnetic energy. The important parameter associated with electromagnetic radiations are the energy is and frequency and wavelength. Energy is directly proportional to the frequency and inversely proportional to the wavelength, is the equation below. We have explained electromagnetic radiation, the association of energy with the frequency, association of energy with wavelength. We have also defined and explained these different terms. The distance between two consecutive crust or trough is called wavelength, and then frequency and energy, the association of these parameters with each other. We have discussed this detail. This was just to refresh your knowledge about the spectroscopy. Like this is the division of different rays according to the frequency, energy, or wavelength. For example, we have a radio waves whose wavelength is like energy is this, energy is increasing in this direction. Microwave whose wavelength is, this is the energy, and wavelength is around this, 10 raised to the power and 10 raised to the power minus 3 infrared. And also what type of response molecule show whenever subjected to, whenever gets subjected to these radiation. For example, radio frequency do nuclear spin transition. So we are using NM. We have developed NMR spectroscopy in this region whenever molecule is subjected to in front of this radiation. Microwave, IR spectroscopy, mostly doing molecular vibration. UV, mostly doing electronic transition. X-rays doing ionization, etc. So coming to the infrared spectroscopy, infrared radiation is largely thermal energy. So consider two atoms which are connected to each other by a bond. Consider this bond as a spring. So this whenever these two atoms are subjected to the infrared radiations, so this bond is an equilibrium bond length in this form. When it is stretched, this when you are applying force, this is like this, and this is in a compressed form. So it induced this infrared radiation induced stronger molecular vibration and covalent bond, which can be viewed as a spring holding together two masses or atoms. Specific bond responds to specific frequencies. Specific frequencies. So these vibrational moods which are induced due to the subjection of these atoms to the infrared radiations, covalent bonds can vibrate in several modes, including stretching, rocking, and scissoring. The most useful band in spectrum, an infrared spectrum, corresponds to a stretching frequency, and those will be focused on in this lecture. For example, this is a stretching, these two atoms, like in H2O, hydrogens is attached to oxygen, and here second hydrogen is attached to oxygen. When these stretch in two different and opposite directions, this is known as a symmetric stretching. And one when in this direction and other in this is anti-symmetric stretching. And also it can go like this. This is known as scissoring or bending. So when a chemical sample, this chemical sample, your analyte molecule, is exposed to the action of IR source, it can absorb some frequency and transmit the rest. It can absorb some frequency and transmit the rest. Some of the light can be reflected back. So when this sample is exposed to the action of IR light, it can absorb some frequency and some is transmitted, and some of the light can be reflected back to the source. From all the frequency it receives, the chemical sample can absorb, retain specific frequency and allow the rest to pass through a transmitted light. And the detector basically detect the transmitted light. So first of all, when IR source is passed through it, means the detector detect the transmittance frequency. But when a chemical sample is placed in the path of, so it absorbs some, the transmitted light is basically reduced. Basically, the detector detect that reduced transmitted light, and by doing also reveals the value of absorbed frequency basically. So basically, when you are representing an IR spectrum, an absorption mode, the IR spectrum is basically this, when this is absorption and this is frequency and wave number. Okay, so wave number is the reciprocal of wavelength. That's why it is written in centimeter inverse. The IR spectrum is basically a plot of transmitted, or here in this case absorbed frequency, versus intensity of transmission or absorption. Frequency appear in the axis unit of inverse centimeter, and intensity are plotted in the percentage, in y-axis in percentage units. So the graph shows a spectrum in absorption mode. So in absorption mode, your spectra look like this. It will be flat until where this molecule showing absorption, like this is the frequency, like 0, 300, 3600. So if this molecule showing absorption in 3600 region, so this will show a peak. But this usually IR spectra is not looking like this, because people are in a different textbook or in a research article, you will not see IR spectra like this. But in fact, IR spectra will be more looking like this. In IR spectrum, this is in a transmission mode, because because it is showing 100% transmission. When a molecule or anything inside that sample container is not showing any absorption, it means that it is 100% transmitting. So the graph shows a spectrum in a transmission mode. This is the most commonly used representation, and one found in mostly chemistry and spectroscopic and research article. So that's why mostly it is given like this. So showing 100% transmitters, 100% transmitters, whenever it shows absorption, it means the transmission is decreased. So it will look like this in, in transmission mode. So keep remember that as IR spectra will always be in a transmission mode like this. So there are different classification of IR bands. For example, means spectra is doing like this here, little bit absorption means so this is a weak band, and this is a medium band which is going to the half of this one, and this is a very strong band like this, when it is going to the almost to the 0% transmit, or means 5-10% transmitters and 80% absorption. So IR bands can be classified as a strong, medium, or weak, depending on their relative intensity and infrared spectrum. A strong band cover most of this y-axis like this, and a medium band falls about half of the y-axis, and a weak band falls about 1/3 or less of the y-axis. So not all covalent bond displays. So we say these molecules are IR active. So not all covalent bond display bands in IR spectrum. Only polar bond do so. These are referred to as IR active. Like this is a strong, medium, weak, and this is not observable in IR. So the intensity of the band depend on the magnitude of the dipole moment associated with the bond in questions. So stronger polar bonds such as carbonyl group produces a strong bands. Medium polarity bonds and asymmetric bonds produces a medium band like this carbon nitrogen, while weakly polar bond like this is a weakly polar bond and symmetric bond produces weak or non-observable, like this is a weak and this is almost non-observable bands in IR spectrum. So infrared bands shapes comes in a various form. Two of the most narrow and broad. Narrow and broad are thin and pointed like a dagger. Broad bands are wide and smoother. A typical example of broad band is that displayed by OH bond, such as those found in alcohol and carboxylic acid, shown below like this. So a typical example of broadband is the displayed by OH bond, such as those found in alcohol or carboxylic acid, shown below. So what information basically we are getting from IR spectrum? IR is the most useful in providing information about the presence or absence of a specific functional group. IR can provide a molecular fingerprint that can be used when comparing sample. If two pure sample displayed the same IR spectrum, it can be argued that they are the same compounds. IR does not provide detailed information or proof of a molecular formula or structure. It provides information on a molecular fragments, specifically functional group, and therefore it is very limited in scope and must be used in conjugation and combination with other technique to provide a more complete picture of the molecular structure. It means that IR spectra is giving you the one sided of the picture, so you have to use this technique in combination with other technique to give you a complete picture of your molecule, about the structure, about the other things of a molecule. So, IR absorption range. The typical IR absorption range for covalent bond is between 600 to 4000 frequency wave number. The graph shows the absorption region of the spectrum where the following types of bond normally absorb. For example, a sharp band around 2200 2400 would indicate the possible presence of carbon and nitrogen between 2400 to 2400, like this, carbon and nitrogen, and would in the possible, or carbon and carbon triple bond is also showing absorption in this region, while nitrogen and hydrogen between this, oxygen and hydrogen between this, this, and this is the and this from 600 to 1400 region is known as a fingerprint region in IR absorption spectroscopy. So although the entire spectrum can be used as a fingerprint for the purpose of comparing molecule, the 600 to 1400 range is called fingerprint region. This is normally a complex area showing many bands frequently overlapping each other. This complexity limits its use to that of fingerprint and should be ignored by a beginner when analyzing the spectrum. As a student, you should focus your analysis on the rest of the spectrum, that is the region to the left of 1400, like this. So you should, this is a fingerprint region, complex, and this is extremely difficult to interpret reliably. So you should focus in analysis there is most stretching frequency occurs, like this is the OH, and this is the saturated carbon hydrogen, like there's your spectrum. So the remainder of this presentation will be focused on the IR identification of a various functional groups such as alkene, alcohol, ketone, carboxylic acid, etc. And thank you very much for today's lecture. So these are the books you can follow: J.D. Christian, Instrumental Analysis, Douglas, Scooge and Crouch, and Wales, Sperling Atomic Absorption Spectroscopy. And thank you very much.